Hi, this is Linear Programming Optimization, and today we will select a problem in trying to find out all the basic solution for the given problems and identify which basic solution is feasible. This is the objective function has to be maximized under the given constraints. We know that it's not standard LP form, so we have to transform it into standard form by multiplying with the negative sign the objective function in order to minimize it, and also replacing the n equal to signs by adding select variables to the left hand side of the uh, constraint equations is x3 and x4 in this case. So we got two equations, four variables. It's an indeterminate case. We know that we will have many solutions, and that's what optimization problems are, where you have a number of solutions and you have to choose the best options or best solutions out of many. And contrary, we have overdeterminate case. Here the equations are linearly dependent on each other, while the condition for optimization problem is that they must be linearly independent. So this is not optimization problem. One more case, if the number of equations equal to number of variables, it will give you unique solutions. Again, it's not optimization problem because it will give you only one solutions and you can't choose the best out of one only. So binomial theorem is used in order to find how many possible solutions can we have for the indeterminate case. Here we have 6 for this particular problem. To plot this on the graph, to have a better visualization, one thing remember is that you can't plot on the graph if there are many variables or more than three variables. But here is we have only x1 and x2, so you can plot it on xy plane much easily as x1 and x2 with the given constraint 1 and constraint 2. One thing more is x1 and x2 should also be greater than or equal or greater than 0. In other words, they must be positive. So we got feasible region over here, and we'll find 6 solutions and trying to see if the solutions lying inside this region or on the boundaries, we call that feasible solutions, and those lying outside the boundaries, we call that infeasible solution. Okay, we have to set some of the variables to 0 and finding the other variables. Those we set to 0 called non-basic variables, and the remaining is basic variables. So solution 1, where x1 and x2 set is to 0 and represent as non-basic variables, the function goes to 0, can be seen from the graph too. Solution 2, where x1 and x2 set to 0, the solution is minus 20, we say much better and smaller than 0. Minus 20 is much smaller than 0. Solution 3 is infeasible because we see that x2 equal to 6 and this point lying outside the feasible region, so it's infeasible. Solution 4, where x2 and x3 set to 0, again it's infeasible solutions because x1 equal to minus 4, and again it's given that x1 and x2 must be positive. Solution 5 is even better, minus 24, which is less than minus 20, and solution, the last one, 6th, is far better, minus 29, and it's the smallest option. And on the graph, we can't go beyond this because going beyond this, we will get out of the feasible region, and the problem or the solutions wouldn't be anymore a feasible solution. One thing you should remember is that we getting minimum values from these solutions, and I have plotted on the graph the max values, because the overall objective is to find the max value, not the minimum. Therefore, we have to plot this on positive side, on the positive axis. Thanks for watching. See you again.